So in this part B of 4.3, we're going to look at several examples. Example 1, use part 1 of fundamental theorem of calculus to find the derivative of f. Okay, f of x is equal to 0 to x square root of 1 plus t to the third dt. So we need to find f prime of x, which is our integrand, square root of 1 plus x to the third. That's all. So next example. Now, g, we have function g. I say here derivative of f. Let's just say derivative of the function. Okay. So g of s is equal to integral from 5 to s t minus t squared to the 8th power dt. So g prime of s, by the fundamental theorem of calculus part 1, will be our integral. The only difference is we see here we start with 5 and not 0. It doesn't matter as long as the lower bound is a fixed number. So our derivative here, it's still going to be, in terms of s minus s squared to the 8th power. Okay? So note, I'm going to make a little note here that g of t is t minus t squared to the 8th power. And when we write here g prime of s, we write g in terms of s. Example 3. Now, big F of x is equal to integral from x to 0, square root of 1 plus secant t dt. So to find a derivative of big F, we need to switch the boundaries because in our theorem we have from a to x. So the lower bound has to be fixed. So to switch the boundaries and have them from 0 to x means we have a negative sign on the front. We had that earlier in section 4.1, 4.2. So everything else stays the same. And now we can say the derivative of big F is the integrand, 1 plus secant, but in terms of x, it will be square root of 1 plus secant x, and the negative sign on the front. So it is pretty simple. If the lower bound is fixed, whether it's 0, 5, or any finite number, and the upper bound is x, you apply the fundamental theorem of calculus part 1 right away. If that's not the case, like in this example here, where h of x is integral from 2 to 1 over x, sine to the 4th t dt. So we have a problem here because the upper bound is 1 over x. This is a function of x, not just x. So we're going to use a substitution here, and we're going to set u equals 1 over x, okay? And then du dx, we're going to need that later, is negative 1 over x squared. So now our function h of x, we can rewrite it from 2 to u, sine a 4th t dt. So we're ready now to take d dx. Trying to get a new page going here. Okay. Here you go. All right. So now d dx of our integral which is the derivative of h, we're trying to find, is from 2 to u sine of fourth t dt. So we have a problem because it's x here and u here. These two have to be the same variable. So we're going to use the fact that ddx is ddu times du dx. So we're going to separate those and put here our integral from 2 to u sine to the fourth t dt. Okay. So now this first part is exactly our fundamental theorem of calculus part 1. So u with u matches. The lower bound is fixed. It's 2, and it doesn't matter if it's 0 or 2 or any fixed number. So we can apply it and say this is sine to the fourth. Now what variable we're going to use is u, the upper bound, okay? So sine to the fourth u times du dx. And now you have to go back to x. U was 1 over x. So we're going to have sine to the fourth 1 over x. And we had du dx right here. That was negative 1 over x squared. And that's our final answer for the derivative of the function. In this case, derivative of h. Okay. More examples. Evaluate. Integral, I'm going to call this a. Integral from negative 1 to 1, x to a power 100 dx. So obviously we have a definite integral, so we're going to use the evaluation theorem, which is part 2 of the fundamental theorem of calculus. So far our examples here, we apply fundamental theorem of calculus part 1. Now we have part 2, which is our evaluation theorem. So the antiderivative of x to the 100 is x to the 101 over 101. Evaluate this from negative 1 to 1. So that is, if you substitute 1, the upper bound first, 1 over 101 minus, then substitute negative 1 to a power. Okay, I'm going to do this again to have more room. So that is equal to 1 over 101 minus negative 1 to a power 101 over 101. So that is 1 over 101 minus. So negative to odd power is negative. With this negative becomes plus. And finally 2 over 101. So part B. Trying to get another page again. Here you go. So integral from pi over 6 to pi sine of theta d theta. The antiderivative of sine of theta, we know it's negative cosine theta. Evaluate from pi over 6 to pi. So that is equal to negative cosine of pi. I'm going to pull the negative sign here, this negative sign here, and then do my evaluation minus cosine of pi over 6. That is equal to negative cosine of pi is negative 1 minus cosine of pi over 6 is root 3 over 2. So after we distribute is 1 plus root 3 over 2. Next example. Integral from 0 to 1, u plus 2 times u minus 3 du. All right, so I have a product and we don't have any formula for integral of product of two functions. So we definitely need to FOIL before we proceed with integration. So we FOIL and it's u squared minus u minus 6 after you FOIL and combine like terms du. So now I have a polynomial and we can find the antiderivative here. So u to the third over 3 minus u squared over 2 minus 6u. Evaluate this from 0 to 1. So first we're going to evaluate it at 1. And so that'll be 1/3 minus 1/2 minus 6. And then we're going to evaluate it at 0. But when we do that, everything will be 0. So that turned out to be negative 37 over 6. Okay, try and get another page. Here you go. Another example. Integral from 1 to 4, 2 plus x squared over square root of x dx. Again, we don't have formula for integrating quotient or product. So what we need to do is break this down to several integrals. So I'm going to divide by square root of x, each term on the top, just like that. So we want to write each part, each term as a power function. And we can do that. So that will become 2x to the negative 1/2 plus, okay, so that will be x squared times x to the 1/2. And that is dx. So you always work on simplifying your integrand first before you can integrate to make things simpler. So again, I'm going to copy this 2x to the negative 1/2 plus x, that will become to the 3/2. And that is dx. So you can integrate all this together or separately. So here our antiderivative is x to the negative 1/2 plus 1 is 1/2 divided by 1/2. Evaluate this, I'm going to do it separate. From 1 to 4 plus the antiderivative of x to the 3/2 is x to the 5 over 2 over 5 over 2. Evaluate this from 1 to 4. And if you continue these calculations, you should get 82 over 5. All right, another example with trigonometry this time. So definite integral from pi over 6 to pi over 2 cosecant t cotangent t dt. Again, we have a product. So we need to do something with this product before we integrate. We're going to rewrite each function in terms of sine and cosine. So cosecant is 1 over sine, and cotangent is, oh, we didn't have to do that because we know that cosecant times cotangent has antiderivative. Okay, so that is negative cosecant. So we didn't have to do this. Cosecant of, I guess, t. Cosecant of t. Evaluate this from pi over 6 to pi over 2. And then we evaluate this. So that is negative cosecant of pi over 2 minus cosecant of pi over 6. So that is negative 1 over sine pi over 2 plus 1 over sine pi over 6. So sine of pi over 2, that is 1. So we have negative 1 plus 1 over sine of 30 is the same as cosine 60, so 1/2. So we have negative 1 plus 2, which is exactly 1. And that concludes this lecture.